Okay, so in the last few videos, I've been focusing on different aspects of this kind of modern tech engine that I've been working on as a hobby project. I talked about things like being able to compile without invoking the macro layer at all, just like built into the engine, the ability to use modern fonts to generate accessible, tagged PDFs, to be able to use the fact that our computers are multi-threaded to very quickly generate, these, in this case, a 98-page PDF, UA2 Gentle, let's pull it up. That is doing all of the usual beautiful typesetting of mathematics and text and all this stuff, almost instantaneously using modern fonts. Here you can see JetBrains Mono and Fira Sans and things like this, and doing so in a way that is, actually tagged so that it satisfies accessibility requirements. So if I look at UA2 gentle.pdf, you can see that this passes the accessibility verifier, right? And then in the second video, I talked a little bit not about the output of these engines, outputting to PDF and HTML, but the experience of working with it and writing the code, the documents themselves, and in particular dealing with error messages. And so, where was it? So I talked about trying to invent a kind of more expressive style of diagnostics, the kind of thing that says, oh, do you have an undefined control sequence? Let me try to find the, closest word replacement that you might have meant. So let me try to be helpful and suggest vec instead of VCE, or C dot instead of C doot, or, say these are where your overfull boxes are occurring, or not only did I need to insert a missing $sign to close math mode, but here's actually where I opened it up. Today I want to talk about a very different part of the tech ecosystem, and that's not working with the outputs or dealing with error messages, but actually the experience of working on the code base itself. And to kind of set this up, I want to talk a little bit about, the original tex.web source code, right? So this was written in a tex.web, in a, the literate programming style, this kind of beautiful, way of interweaving explanations and code so that you can explain the what and the why and the how of everything that's happening in a way which lets you separately compile documentation and the program, and it's this wonderful way of writing software. On the other hand, I think it's undeniable that the Tech82 codebase almost needs this literate programming style to help anybody understand what's happening, right? Famously, the tech codebase is this, difficult to reason about thing, at least for, mere mortals like me, where, you're using this kind of macro spaghetti so that any function can reach in and mutate the global state arbitrarily far away from whatever procedure you're working on at the moment. There's, lots of this kind of confusing amount of total context you need to hold in your head in order to reason about what the program is doing at any moment, right? And one of the things that I want to emphasize is that a lot of the style that this was written in was based on the constraints of both, the compilers for Pascal at the time and the hardware that was available, right? And when trying to modernize this engine, I've tried to think hard about, freeing ourselves from some of those constraints because, language standardization has happened and we know a lot more about hardware. I mean, I know that there are 8 bits in a byte in a way that Knuth could not even, rely on at the time. And so let me first just kind of highlight a few kind of comments in this document that I find kind of amusing, and then I'll kind of try to go back and forth and show what some of the original tech code looked like, or at least the C translation of it, and then I'll try to show how, my engine is trying to do something that's, I think, a little bit more developer-friendly. Okay, so one of the first things that I'll try to do is find this string here where this is part of the output routine where, tech is writing bytes to a DVI file. And, one of the comments here is that, one of the reasons that we're using a macro here instead of, having a function that's doing this for us is to avoid paying the cost of invoking a procedure. Right, nowadays, we're very used to aggressive optimizing compilers that will happily inline functions for us and things like this. And that just wasn't the case, in the late 70s, early 80s. And so, having this be a function instead of a macro might have meant, an expensive function pointer, putting variables in the call stack, something that would really have slowed down, tech, right? And, obviously these kind of macros appear literally everywhere in the source code, and you have to keep track in your head of, okay, global variables and being able to jump from one part of the code to the other with these macros, to say nothing of the sheer number of go-to statements, scattered throughout this code base. Okay, let's see. Even Knuth admits that some of this literate programming stuff is pretty cryptic. Here I wanted to highlight this. It's 11 lines down. This string right here because it's a beautiful set of data. One of the things that's so amazing about working with the output of tech is the beautiful typesetting of mathematics, and all of the or at least most of the rules for encoding how mathematics spacing works is encoded in this string. And you can see this up above here. In this string, 0 means don't add a space between something. 1 means add a conditional thin space, and so on and so forth. And, you can't even find the explanation in the tex.web source. You have to separately read a different piece of documentation to understand, what is supposed to happen. You're just supposed to know that this string is helping make it happen. And notably, look, if Pascal had provided a good way to preload constant arrays, this part of the program would not have been so strange, right? Maybe one of the things that I wanted to highlight was the fact that even when people have tried to write things in more modern languages, they often still rely on the original macro style and this kind of stuff, even though more developer-friendly options are available to them. Let me see if I can pull up the Literate version of this. I think it's called initialize math spacing. Initialize math spacing right here. And you can see that this is doing, in some ways, let's say heuristically, the same thing that magic string was doing, except it's doing it in a macro style, right? So it's saying, I'm going to have blocks of, things related to the ORD type of math unit, operators, opening and closing things, punctuation, stuff like this. And so for each of these blocks, I'm going to declare, with the aid of some macros, that themselves rely on other macros, that themselves rely on other macros. So you really have to kind of unwind a lot of mental stack in order to understand what's really happening. But it's kind of setting up this, this array of how is spacing supposed to happen between an ORD and whatever the next thing is. The next thing is an op, but you have to know that, right? An ORD and an op. On the other hand, we in C++, in many languages, you can declare constant preloaded arrays. That's not a problem. And so you can, let's see, in math helpers, instead you can just take exactly that same magic string, but represent it in a way that it's kind of transparent what the meaning of that string actually is. This is a table related to mathematical spacing. The row and columns mean the specification of the kinds of mathematical elements that you're putting adjacent to each other, and then you can just use some function that kind of helps you access that table and tells you what kind of glue are you supposed to put in between these different mathematical elements. Right? Let's see, maybe one other example that I want to talk about where the kind of constraints of the compiler and of the hardware and of the language specification makes it a lot harder, in my mind, to read the code and understand what it's doing. Let me switch over to this, I think, remarkable TeX's project. This is by Aronson. So here's the README. Maybe I'll try to remember to put a link to this repo in the description because I think it's really quite remarkable. It's basically taking the tex.web, Pascal plus documentation, and instead doing it in C and Markdown. So it's just like a very convenient format to read these things in. And for our purposes, it means that we can look at the Pascal code, but the C version of the Pascal code, which for me is easier because I don't know Pascal, and also it means that we can get nice syntax highlighting. Right? So one of the things that I wanted to look at was the arithmetic routines. Right? So first, let me go ahead and turn off these LSP warnings because they're a little bit hard to work with. Knuth had to deal with the fact that a lot of things that we take for granted now were not really fully specified. Not only this thing about how many bits are in a byte, which continues to just blow my mind, but also things like, it would be compiler specific which way truncation after integer division worked, right? And so Knuth was very careful to have these routines that said, I'm gonna do, rounding and half of integers or things like that in, excruciating detail so that I have complete control over exactly how many pixels, how many scaled points, how much space was going to be in any particular location. And maybe one of the things that I want to look at is this, I think it's called xn over d. Xn over d is a function that calculates, a product divided by something. And, if you read through this, I would argue it's not that hard. It's not that easy to kind of reason about. You can see that there are these magic numbers. I mean, they're magic numbers that are powers of 2, so you can kind of work out what they're supposed to be eventually. You can see that it's kind of not a self-contained function. There's this arithmetic error, which is a global variable that this function is able to change. One of the reasons for that is because in early Pascal, the return value of a function had to be a single primitive type. So rather than this thing returning, here is the result of the division, and here is whether there is an arithmetic error or not, it had to return only one thing and then mutate something else, right? And actually, you can see here there's this also remainder global variable where the thing that we're returning is going to be the quotient, and the remainder is going to be a global variable that's set and could be read by the caller of this procedure or not. We have no way of knowing. And what was this arithmetic error about? It's because we're trying to multiply a scaled number, that's an integer in this implementation, by another integer. And Knuth was worried about, well, what happens if there is integer overflow? We want to be able to catch that and flag that and make sure that an arithmetic error gets set if there's overflow between these things. And so all of this kind of, modding out by some power of 2 and then doing some extra work is all because, is all because it's hard to know when the multiplication of an int by another int basically was going to require more bits, right? Whether there's going to be an overflow. And this is another example where, we have language standardization now, right? So the way truncation works, do you round up or do you round closer to 0 or, this kind of thing? That's now part of the language specification, right? C99 or I think it was C++11 that specified it for that, right? So we don't have to, dance around the fact that we don't know how our compiler is going to work with these, fixed point operations. So we can write much simpler code. So let's go ahead and look at, source utilities fixed point math. First we can define, structures that have the information that we're interested in, right? So we can return not just a single primitive type, but we can return a quotient and a remainder and an overflow value. So we don't have to mutate global state. And what was it called? Xn over D. I think this function is just much easier to reason about. What is this thing doing? Well, it's computing the product of x and n, and a single IDiv instruction, I'm going to compute both the quotient and the remainder. And if the quotient is something that overflowed, how big a single scaled type can be, then I need to throw one of these. I need to say that there was an overflow error. Otherwise, everything was fine. And I don't know, there's just, there's a lot less worrying about magic numbers. I wonder if the badness thing is in here. Yes, it is. Here, this thing about how do I compute badness? This is part of the line breaking algorithm, and it tells you, given how much you had to stretch or compress spaces between words and paying penalties for inserting hyphens and things like that, how should I compute the badness, the badness of a line? And reasoning about exactly what this is doing is maybe not the easiest thing to do, even with some of these inline comments that tell you that 297 cubed is very close to 100 times 2 to the 18. And one of the things that we can do, I think I called this compute glue badness, is to say, really, what are we trying to do? Well, we are going to do the same multiplication of the numerator by something, and that's because what we're representing is 100 multiplied by the ratio of something cubed, and indeed that 297 comes from 64 multiplied by 100 to the third root of 100. But then all I'm really doing is kind of saying, okay, if I've come up with a numerator which is too large, I want to return this infinite badness kind of penalty, and then otherwise I'm just doing this work. And okay, here, I guess I left the magic numbers, but I just included some explanation up here. Okay. Actually, speaking of line breaking, maybe the last thing that I want to talk about before wrapping up a little bit is this question of, the fact that TeX is written the way it is, where you have these procedures and they're constantly mutating global state, I think sometimes even detracts from the beauty of some of the underlying algorithms. And so if I look at for instance, the try break function. Try break function, again, let me silence those warnings. This is like the heart of the Knuth-Plass optimization for deciding where do you break a line, right? I have this paragraph, there's any number of places that I could break it at a space or insert hyphenation points or things like that, and how do I evaluate, the most pleasing shape of a paragraph given these constraints in, a reasonable algorithmic complexity, right? Knuth-Plass is this beautiful dynamic programming like solution to that problem, and it is hard to actually see through this code what the Knuth-Plass algorithm is actually doing, or where that algorithm really exists, as opposed to the parts that are interfacing with, the rest of TeX memory. So if you scan through this code, there's you have an infinite while loop with some, labels and go-tos that you're jumping between. The Knuth-Plass algorithm knows about a specific kind of node, nodes in maybe I'll talk more about how TeX manages its memory in a future video, but very specific, not to this idea of I have elements that occupy space and there's different places that I can arrange them and this kind of outline of the dynamic programming problem. No, this implementation knows about all of the details of TeX model of memory, and it knows, what line we're on and all these things. And I don't know, do all 6, what does do all 6 even mean? Well, it's doing this function to something else, 6 different elements of it. It's related to, how much stretchability there is in the glue and stuff like this. Again, the algorithm knows the details about the types of memory representation TeX has for different structures. And not only does it make it hard to understand where the logic of Knuth-Plass really is, but it also makes it very hard to generalize what's happening. A major goal of the TeX community for a long time has been imagining applying the Knuth-Plass algorithm, not just to line breaking a paragraph, but to, page breaking. Let me take not a bunch of horizontal boxes and arrange them correctly into lines, but take a bunch of vertical boxes and arrange them with the same kind of logic, but into different pages. And one of the things that's so hard about that is that the way this algorithm is written is deeply entangled with walking through TeX underlying memory of, words and glue and hyphenation points and things like that. And, we can try to do something that's a little bit different. So we can try to, say, there's going to be a part of this program, the line breaking part of the program, which is responsible for walking through TeX memory and, figuring out, okay, here is, let's say, a box corresponding to a word or a space or a hyphenation point or whatever, and arranging it into a form which is capable of then just being handed off to something which is, ignorant of all of the rest of TeX. So, you could have a Knuth-Plass optimizer, which doesn't know anything about the underlying TeX engine, doesn't know anything about TeX, array of nodes or memory words that make up the different flavors of nodes that it knows about, something which really just says, I have a concept of, a break item, something which, it's a word, it's a space, it's, something where there's constraints about when I am or am not allowed to break around it, and I can try to just directly implement what the Knuth-Plass algorithm is. And what that is, involves setting up a little bit of shared context, and then saying I have a bunch of active nodes. Active nodes in the nomenclature just mean as I'm working through potential partial solutions as I build up this paragraph, active nodes are feasible partial solutions to the full dynamic programming problem. I can just say, let me go through those active nodes, process them to try to do something, and then, if I find something where I'm satisfying some criteria for how bad the line breaking is, let me try to promote things that I'm tracking into an active node list for the next pass. And then at the very end of this, I can then go ahead and say, given everything I know, let me go ahead and try to find, okay, for this subproblem, what is the node that has the lowest overall demerit or badness score? If I can find that, satisfying other criteria, great. If I can't, maybe shift what your criteria is and do the same thing again. I think this is a style of programming where, I could add a lot more documentation to this code, and I really should. But I think a lot of the motivation for literate programming was because the constraints of the day meant that it was hard to express what your code was doing without having this kind of detailed log notebook from a genius to accompany you. Right? And one of the reasons that I've been so interested in this aspect of modernizing it, not just like taking the syntax and translating it to C and sprinkling a little bit of C++ 20 on top of it or whatever, is because I think really taking the time to refactor and find the seams between these algorithms, I think will ultimately be very good for the open source stability of this project. One of the things that I think TeX suffers from is that it is so hard to work on these code bases. Certainly, basically nobody is working on, change files that then, apply to the original TeX.web and then get fed through the, web to C conversion pipeline. It's a very, old-fashioned style of programming that increasingly few people know about. The LuaTeX version of TeX, I think, is remarkable, and I think there's a lot of things that it's doing fundamentally right. But at the same time, it's also not easy to contribute to the development of that. And so, one of my hopes was that by having a TeX engine that kind of looked more like what modern programming looks like to most developers, we could really help, kind of harness some of the open source energy in the community. All right, so I think that's plenty for today. If you have any questions, of course, feel free to let me know in the comments or send me a message. And until next time.